Let's talk about series versus parallel circuits. Series, parallel. Let's say they both have 5-volt batteries and each resistor is 10 ohms. So we're going to calculate the voltage drop across each resistor and we'll calculate the current. We can replace the series resistors as one resistor of 20 ohms and then find the current. And we see that we have 0.25 amps flowing through this circuit. What's the voltage drop across each resistor? We don't know that number. That would be the voltage drop from here to here. We do know that the current is 0.25 amps and the resistance is 10 ohms. So the voltage drop is 2.5 volts from here to here. This exact same math would be applied here. So the voltage drop across the next resistor is also 2.5 volts. So we can see that we're going to have a current flowing of 0.25 amps. It's the same amount of current everywhere in the circuit. There's no other place for that current to go. And the potential energy gained of 5 volts will be lost across the resistors. Since they're equal resistors, we're going to lose 2.5 volts and then, of course, another 2.5 volts to get back down to 0. How does that compare if we're hooking up our resistors in parallel? Well, the voltage this time is going to be the same here, here, here. It's all the same voltage. We are at 5 volts. And then over here, we're at 0 volts, and it's going to be 0 volts all along that wire. We don't lose any voltage along a wire. So that means the voltage drop across that resistor is 5 volts. So if we say V equals IR, we know that the voltage drop, technically we don't always put the delta sign, but that's okay. 5-volt drop equals the current times the resistance of 10 ohms. And I didn't have to put the resistors together to come up with the equivalent resistance. I just know that the voltage across here is 5, so I was able to do this directly. And the current through that resistor is going to be 0.5 amps. That's going to be the same current through this one because both resistors have the same voltage across them. So we're going to have 0.5 amps going through this resistor, 0.5 amps going through that resistor, and therefore we're going to have a current coming out of here of 1 amp. And then it'll be split into two, 0.5 amps and 0.5 amps. Now let's try a series circuit where the resistors are different. So the first thing we'll do is calculate the equivalent resistance of the circuit. And that's going to simply be, it's really easy, just add them up because it's in series. And then how do we calculate the current going through this circuit? Well, now we're going to look at these 2 points and say, what is the voltage drop across there? And I'm going to say V equals IR. So between these 2 points, we're going to have the full 5 volts. We're gaining 5 volts, we're going to lose 5 volts. And then we're going to calculate the current, and the equivalent resistance is 20 ohms. And there we have the 0.25 amps for the current. Now, what about the change in voltage across each one of those resistors? Well, we can say that the voltage drop for this resistor is I times R. And we know that the current is 0.25 amps. It can't go anywhere else. There's 0.25 amps coming this way. It's going to go through both of those resistors. So we take the 0.25 amps here, multiplied by the resistance, 15 ohms, and we get the change in voltage. And we get 3.75 volts. That's across that resistor. Now, what about the rest of the voltage drop? Well, we could do the same exact equation again for this resistor here, where we can say the change in voltage is equal to 0.25 amps times 5 ohms. And that's going to give us 1.25 volts dropping across that resistor. Well, I think that makes sense because if this resistor, we lost 3.75 volts, we're going to have to lose 1.25 volts to complete the drop of 5 volts. Those voltages lost will be equal to the voltage gained when going around the loop. Alrighty, now we have the two different resistors hooked up in parallel. How are we going to calculate the current going through each one of those resistors? If this is 5 volts, then along this wire, since it's a conductor, we're not going to lose any voltage along that wire. I'm going to be at 5 volts here. On the other side of the resistor, it's connected to this side of the battery, which we will say is at 0 volts. So there, again, this is a wire. There's no difference in voltage along that wire. We're at 0 volts here. So I know that the voltage drop across that resistor has to be 5 volts. So I'm going to go V equals IR, and I'll say that my voltage drop is 5 volts, and the current is what I'm looking for this resistor, and R1 is 15 ohms. So the current going through here is going to be 1/3 of an amp. Now, what about over here? We're going to have to do the same exact thing. I know that the voltage here is 5 and 5 and 5. You don't lose voltage along the wire. And down here, we're at 0. So we're going to say the same thing. Change in voltage equals I times R. And that's going to be 5 volts. And then we're going to have I2, and this is 5 ohms. And so I2 is going to be 1 amp. Now, where is all that current coming from? It's coming from the battery. The current is charge per time. It's a certain amount of charge flowing out of that battery. It better be 1 1/3 amp. And 1/3 amp will be flowing through this resistor, and 1 amp will be flowing through that resistor. It's based on conservation of charge. That's your junction. What comes into the junction comes out of the junction. Well, you've probably heard people say that current will take the path of least resistance. That might have you believe that all the current would go through the lower resistor and none of it would go through here. We can see with the math that that's just not the case. The analogy that's good for this would be, say, for example, a highway where we have a wide number of clear lanes and most of the traffic will flow that way. And there may be one lane open over here. Some cars will go that way. They're all not going to go through the lowest resistance. So to summarize, in a series circuit, there's no other place for the current to go. The current going through the first resistor equals the current going through the second resistor. When we look at the voltage drop across each resistor, whatever this drop is and whatever that drop is, they have to add up to the voltage of the battery in the series circuit. And in the parallel circuit, we have to say that the current coming out of the battery is split going into each resistor. And so we'll say the current coming out of the battery is equal to I1 plus I2. And the voltage drop across each one of these, they're going to be the same. This voltage here is going to be the same here. Voltage 0 over there. So the voltage drop across parallels are the same. As you can see here, with the series, the currents are the same. Here, the voltages are the same. Here, the voltages add up, and here the currents add up. You can combine both ideas of parallel and series circuits to form a compound circuit. And when you do that, the first thing we're going to do is solve for the equivalent resistance of this circuit. You can redraw the diagram to simplify it. For example, we can take this resistor, which is in series with this parallel unit. We'll replace the parallel unit with one resistor. If you use the formula for parallel resistance, you get 4 ohms. So now we have 10 ohms. So we can now combine these into a single resistor of 14 ohms. So the equivalent resistance of this circuit is going to be 14 ohms. Now we're going to find the current in the 10 ohm resistor. Well, that's going to be the same current that's coming out of the battery. Well, that'll be the same current then that's going through this simplified circuit. So if I write that we have a resistor of 14 ohms here, I'm going to be able to calculate the current going through this circuit. That's going to be 5 volts dropped across that resistor, and we solve for the current. And that works out to be 0.357 amps everywhere in this circuit. And that's the same as the 0.375 amps coming out of here and going through, there's no other place for it to go, the 10 ohm resistor. So we have 0.357 amps. Now what about that voltage drop across the 10 ohm resistor? We can again apply V equals IR to it. We know what the current is, it's 0.357 amps. We know the resistance is 10 ohms. So what's going to be the voltage drop across that resistor? 3.57 volts. And that's the answer for that question. What's going to be the voltage drop from here to here? That's what we're asking here. That's the same as the voltage drop from here to here because these are wires and there's no voltage drop across there. So from here to here, we're going to have to calculate the voltage drop. Well, if we lose 3.57 volts from here to here, we have to lose the rest from there to there. So across this whole span, we have a voltage drop of 5. And we saw that across here, we have a voltage drop of 3.57. Then the remaining voltage drop has to occur. 1.43 volts. So we have 1.43 volts across the 5 ohm resistor. What is the current going through that 5 ohm resistor? Once again, we're going to use V equals IR, and the voltage drop across there we now know to be 1.43 volts. We don't know what the current is. We know the resistance is 5 ohms, and we're going to calculate the current. We get 0.286 amps. So that's how much current is going to be flowing across here. I'll call that I1. Here we have an I2 then. How much current's going there? Well, the current going through here was 0.357. And it's going to have to split and go through each of those. So the current going into this junction is going to be 0.357 amps. The current coming out of the junction has to be the same. And the current going through the top resistor is going to be 0.286 amps. And then we can solve for the current going through the bottom resistor. And I get 0.0713 amps. In the calculator, you'd carry some extra digits. So we can see that, does this check out? What could I do? I can take that current, look at this resistance, and say, what is the voltage drop across that resistor? This is just a check now. We're going to go 0.0713 amps times 20 ohms, and I get 1.43 volts dropping across that resistor. That's the same drop as this is up here, and it should work out that way. So what can we say in summary about the compound circuit? Well, maybe for one, the voltage gain from that battery has to be equal to the voltage loss through all the resistors. 2, the current going into a junction has to be equal to the current coming out of a junction. We could say that the voltage across a parallel resistors, they're the same for each one of those resistors, that voltage drop. So I think that pretty much sums it up. You can always simplify the diagram. Replace resistors and get it down to just one resistor to start off with.